1.4 Operations on sets. We have operations on sets, intersection, union, and difference, which is sometimes called minus. We can have this kind of notation on the left and express the same idea on the right. A intersect B means the set X such that X is in A and X is in B. A union B is the set X such that X is in A or X is in B. And A minus B is the set X such that X is in A and X is not in B. It might be easier to think of these operations in terms of Venn diagrams, which I will show here. So for A intersect B, you want to think about the section where A and B overlap, because X is in A and X is in B. So it's going to be this spot in the middle. Now for A union B, you want to show that X can either be in A or X can be in B. So you might think that we might only color in the spots that doesn't have the intersection, but actually the union of A and B is the whole thing. And now for A minus B, you want to think of it in terms of you take all the things that are in A and you take out anything that was in B. Well, taking out anything that was in B is taking out this intersection right here. So the only part that we're going to have of A minus B is right here. Now for a more complicated example. So here we have A union B minus A intersection B. And this is a more complicated operation called the symmetric difference. And the symmetric difference can show up in two ways. It could show up as what I just mentioned here, or it could be A minus B union B minus A. And these notations are really the same thing in terms of the Venn diagrams. So to think about it intuitively, what we have here on the left side of the minus is A union B. So first we start with the entire part of A union B, all the things that are either in A or B. And then you take out, which is what this slash means, whatever was in A intersect B. So we take out whatever was in the middle here. And that looks like this. Now for the other way to express it, it's the union of A minus B union B minus A. So let's think about A minus B, which we have above over here. And so it's just the left side. So we're going to take that part. And then we're going to union it with B minus A. So whatever was in B, but you take out the part that was in A. And there you have it. This shows that the two forms of the symmetric difference are the same. And you might see the symmetric difference expressed in terms of this triangle here. Now we're going to move on to some examples. This is example 1.4.4 from the textbook, and I'm just going to do part 3. The question is, analyze the logical form of the following statement. When they say analyze the logical form, you might think, what the heck does that even mean? At least that's what I thought. What they want you to do when they say this specific direction, it means that you need to show what it means for X to be an element of the union of A intersection B and A intersection C. And we need to refer back to our set notation at the beginning, this right here, and then use it in our problem. So back to part 3. So X element of A intersection B union A intersection C. So first we want to think about this union. So this union is kind of equivalent to an OR. So X is in A intersection B, or X is in A intersection C. And our reasoning is definition of union. And now our next step is to kind of decipher what it means for X to be an element of A intersection B. And we just demonstrated that above already. So which that means X is in A and X is in B. And we're going to do the same thing for the right side. So we have X element of A and X element of C. And our reasoning behind this is definition of intersection. So you see here our parallels between OR and union and intersection. Now for 1.4.5, part A. It wants us to verify this identity by writing out, using logical symbols and the equivalence laws, what it means for an object X to be an element of each set. So what we want to do when we need to show that things are equivalent is that we need to take what's on the left side of the equality and then show through a series of steps somehow that becomes what's going to be on the right side. So let's start with the left side here. So we want to show that X, some arbitrary element X on the left side. So we're going to write X element A minus A intersect B. And now we're going to use our definition of minus. X is an element of A and X is not an element of A intersect B. And this is our definition of that. Now we're going to sort of think about what that means for this inside here. So we're going to express that not an element of inside here. A and X non-element of B. So in a way, you could think that we sort of distributed this negative, this not an element of in, because alternatively, we could have also written it as not X element of that. Oh, and when we wrote it that shows that this should be an OR by De Morgan's law. Okay, so now we have a something on the outside and then something on parentheses of two things on the inside. So we're going to do distributive law. So now you might notice that on the left side we have a contradiction here because we have an and. X is an element of A and X is not an element of A, and that's not possible. So The key thing that you need to notice here is that this is a contradiction. Therefore, we need to look at what our contradiction laws say. And if you look back at the contradiction law, it states that if you have P, this thing on the right side, for example, ORed with a contradiction, it's going to be equivalent to whatever P is. So in a sense, by the contradiction law, the contradiction kind of cancels out because we have an OR, and then all we're going to be left with is whatever was left here, P. So this is going to sort of cancel out. So we just have X the element A and X non-element of B by contradiction law. I know that I didn't go over it, but it's good to look back in your textbook about it. And now we think about, oh, X is an element of A and X is not an element of B. That identity looks kind of familiar. If you look back at our laws, or our operations, that's actually the definition of A minus B. X is an element of A and X is not an element of B. So we can write X element of A minus B, and that's and there we have it. We showed that X is an element of A minus A intersection B is the same thing as X element of A minus B. And now for our last problem, which should go by pretty quickly. Okay, so 1.4.6, use Venn diagrams to verify the following identities. So we have A union B minus C is equal to A minus C union B minus C. So here we have something a little bit different in which we have 3 circles, and we just need to show that their Venn diagrams are the same. So first, let's start with the left side of the equality. So you have A union B. So let's do that. And then we have minus C. So we're going to take out any portion that overlapped with C, and that's going to be these over here. So I'm going to just erase that. Oops, let me just redraw these. Okay. And now we also have what's on the right side. So we're going to do A minus C. That includes this overlap part with B because nothing changed with that. Union of B minus C. So B minus C is also going to be like this. So again, we have that their Venn diagrams look the same and that we verified these identities.